Somewhere in a suburban backyard right now, a golden retriever is doing something that makes absolutely no sense. She has a rawhide bone in her mouth, a full bowl of kibble sitting untouched on the patio behind her, and she is digging. Her front paws work the soil in rapid, alternating strokes, sending mulch across the flower bed until she has carved a hole roughly the size of a cereal bowl. She drops the bone in, pushes dirt over it with her nose, pats it down twice, and trots back inside to sleep on a $60 orthopedic bed next to a climate-controlled heating vent. She will never be hungry. Not once in her entire life. Her next meal is 12 hours away at most. There is no predator coming to steal her food. There is no winter approaching that will freeze the ground and make foraging impossible. And yet she buried that bone with the same urgency and precision that her ancestors used when their survival depended on it. That was the behavior. That was 2024, in a house with central air and automatic feeders. Now rewind the clock 20,000 years to a frozen river valley in what is now southern Siberia, and the same sequence of muscle movements is happening in a completely different world. The animal doing it is not a pet. She is a gray wolf, roughly 40 kilograms of lean predatory machinery, about the weight of a 10-year-old child. And for her, burying food is not a quirk. It is the difference between surviving the next 3 weeks and starving to death on a frozen plain, where temperatures drop to minus 50 degrees Celsius, cold enough to freeze exposed skin in under 2 minutes. This decision seems small at the time. It wasn't. The wolf has just eaten. Her pack brought down an elk 2 days ago, a bull weighing over 300 kilograms, roughly the mass of a grand piano. For a pack of 8 wolves, that is perhaps 35 kilograms of edible meat per animal. But a wolf's stomach can only hold about 9 kilograms at maximum capacity, roughly the weight of a large bowling ball. The math creates a problem. There is more food available than any individual wolf can consume in one session, but in 3 days the carcass will be picked clean by ravens, foxes, wolverines, and other scavengers. The surplus exists right now. It will not exist soon. So she caches. She tears a chunk of meat from the rib cage, carries it 400 meters from the kill site, far enough that the scent cloud around the carcass will not lead competitors to her stash, and buries it beneath the snow. She returns, takes another piece, walks in a different direction, buries it in a separate location. Over the next several hours, she distributes her surplus across multiple sites, each one isolated from the others, each one memorized. If a wolverine finds one cache, she still has 4 more. This is not mindless instinct. This is spatial strategy. And the wolf brain executing it has been shaped by roughly 2 million years of canine evolution. A span of time so vast that if you compressed it into a single calendar year, the entire history of human civilization would occupy the final 90 seconds before midnight. The behavior biologists call food caching is one of the most ancient and deeply embedded survival strategies in the canid lineage. Wolves, coyotes, foxes, jackals, and African wild dogs all do it. The motor pattern is remarkably conserved across species. Dig with the forepaws. Place the food item. Push loose substrate over the item with the muzzle. Pat or press the surface flat. Walk away without looking back, because looking back attracts the attention of observers who might raid the site. In 1947, ethologist Konrad Lorenz at the Max Planck Institute for Behavioral Physiology described this type of behavior as a fixed action pattern. Once triggered by the right stimulus, usually the presence of surplus food, the entire sequence runs to completion. You cannot interrupt it partway through. You cannot teach the animal to skip a step. The motor program is encoded so deeply in the neural architecture that it operates below the level of conscious decision-making. And that is exactly why your golden retriever still does it on a Thursday afternoon in a fenced backyard with a subscription dog food delivery arriving every 2 weeks. But to understand why the behavior survived domestication, you need to understand what domestication actually did, and what it did not do. The story of how wolves became dogs is one of the longest genetic experiments in the history of life on Earth. Molecular geneticist Robert Wayne at the University of California, Los Angeles, published work in the late 1990s and early 2000s using mitochondrial DNA analysis to estimate that dogs and wolves began diverging genetically somewhere between 15,000 and 40,000 years ago. More recent ancient DNA studies, including a 2020 paper by Anders Bergstrom and Pontus Skoglund at the Francis Crick Institute in London analyzed genomes from ancient dog remains across Eurasia and confirmed that by 11,000 years ago, at least 5 distinct dog populations already existed across the globe. The divergence had happened much earlier. The most widely accepted model of how it began is not dramatic. There was no ancient hunter who wrestled a wolf pup into submission and declared it a pet. The process was almost certainly self-initiated by the wolves themselves. Picture a late Pleistocene human encampment. Scraps of bone and meat accumulate at the edges. For a wolf, this is a food source that requires zero hunting effort. But approaching a human camp is terrifying for most wolves. The boldest ones, the least fearful, the most tolerant of proximity to an alien species, were the ones who ate. And because they ate more reliably, they survived winters that killed their shire packmates. Their offspring inherited the reduced fear response. Over hundreds of generations, the wolves who lingered near humans became genetically distinct from the wolves who did not. They became smaller, their skulls shortened, their teeth shrank, their coats diversified. Their brains actually decreased in size by roughly 20% compared to wolves, a reduction roughly equivalent to losing the volume of a tennis ball from the cranial cavity. This last detail is significant. A smaller brain does not mean a stupider animal. It means an animal whose neural architecture has been reshaped by different selection pressures. Wolves need massive spatial memory to navigate territories spanning 500 square kilometers, an area larger than the City of London. They need sophisticated pack coordination for hunting prey 10 times their size. They need constant predator vigilance. Dogs needed none of those things. What they needed was tolerance. Tolerance of humans, tolerance of crowding, tolerance of unpredictability. The cognitive hardware required for independent survival in the wild was no longer under selection pressure. So it drifted. It softened. Whole circuits that once governed fear response, territorial aggression, and long-range spatial planning were relaxed by the absence of the survival demands that had maintained them. But the caching behavior was not among the circuits that disappeared, and the reason illuminates something profound about how evolution works. Natural selection is efficient at building traits when there is strong, consistent pressure favoring them. An animal that caches food survives famine. An animal that does not dies. Over thousands of generations, the caching behavior becomes nearly universal in the population. The neural circuitry supporting it becomes deeply embedded, wired into the brainstem and basal ganglia, the ancient subcortical structures that operate below conscious awareness. But natural selection is remarkably slow at removing traits when the pressure disappears. If a behavior no longer provides a survival advantage but also does not cause harm, there is no mechanism to eliminate it. The dog that buries bones in a backyard is not losing food, is not attracting predators, is not wasting energy in a way that reduces reproductive success. The behavior is neutral, and neutral traits persist. Geneticist Dmitry Belyaev demonstrated this principle with extraordinary clarity in an experiment that began in 1959 at the Institute of Cytology and Genetics in Novosibirsk, Siberia. Belyaev selected silver foxes exclusively for tameness, breeding only the calmest, least aggressive individuals each generation. Within 10 generations, fewer than needed to fill a school classroom with distinct ancestor-descendant pairs, the foxes began showing physical changes that Belyaev never selected for: floppy ears, curled tails, piebald coats, shorter snouts. They wagged their tails at humans. They sought eye contact. But here's the detail that matters for the caching question. Even after 60 generations of selection exclusively for tameness, even after the foxes had become functionally dog-like in their social behavior toward humans, the food caching instinct remained intact. Lyudmila Trut, who continued the experiment after Belyaev's death in 1985 and maintained the breeding colony into the 2020s, observed that tame foxes still cached food when given surplus. The behavior was never under direct selection in the experiment, either for or against. And so it simply persisted, undisturbed, like a file on a hard drive that nobody ever opens but nobody ever deletes. This is where the timeline stops making comfortable sense. Your dog's caching behavior is not a recent leftover from the last few thousand years of domestication. It is a survival program that predates the divergence of wolves and dogs entirely. It predates the genus Canis. Fossil evidence from canid ancestors in North America, dating back roughly 35 million years, shows tooth wear and skeletal morphology consistent with predatory species that would have experienced seasonal food scarcity. The caching instinct may have been refined in wolves, but its roots are so ancient that virtually every member of the family Canidae on Earth still exhibits some version of it. 35 million years. That number is so large it resists comprehension. If you converted those years into seconds, you would be counting for over 1,000 years without stopping. The behavior in your dog's brain has deeper roots in evolutionary time than the Rocky Mountains have in geological time. The Rockies began forming about 80 million years ago, but reached their current height much more recently. The caching program in your dog is older than most of the landscapes you have ever seen. Now consider what happens inside the brain when the behavior activates. Neurobiologist Jake Panksepp at Washington State University spent decades mapping the emotional circuits of mammalian brains. His work, published extensively through the 1990s and 2000s, identified what he called the seeking system, a dopamine-driven motivational circuit that generates feelings of anticipation, excitement, and focused engagement. The seeking system does not care whether the goal is achievable or rational. It cares about the search, the pursuit, the act of working toward a resource. When a dog buries a bone, the seeking system is active. Dopamine floods the mesolimbic pathway. The animal experiences something that Panksepp argued was functionally equivalent to what humans feel when they are enthusiastically working toward a goal. Not satisfaction. Not relaxation. Eager engagement. The digging, the placing, the covering, each step of the motor sequence triggers a small neurochemical reward. This means the dog is not caching food because she expects to need it. She is caching because the act of caching itself feels good. The behavior has been decoupled from its original survival function, but remains coupled to the reward system that once reinforced it. The food scarcity is gone. The dopamine is not. And this decoupling explains something that puzzles many dog owners. Dogs frequently cache items that have no nutritional value whatsoever. Tennis balls, socks, television remotes, children's toys. The trigger for the behavior is not hunger. It is not even food, necessarily. The trigger appears to be the possession of a valued resource, combined with the absence of immediate consumption pressure. If a dog has something it values, but is not actively consuming, the caching program activates. The muzzle push, the covering motion, the walking away. Owners have watched dogs perform the entire burial sequence on a hardwood floor, pushing invisible dirt over a chew toy with their nose, patting down a surface that cannot be patted. The motor program runs to completion regardless of whether the physical environment supports it. Adam Miklosi, head of the Family Dog Project at Eötvös Loránd University in Budapest, has studied canine cognition for over 2 decades. His team's research, published across multiple papers in the journal Animal Cognition and elsewhere, has mapped how dogs adapted cognitively to life with humans. Dogs evolved the ability to follow human pointing gestures, something wolves cannot do even after extensive socialization. Dogs developed a left gaze bias when looking at human faces, focusing on the right side of the human face, where emotional expressions are most visible, the same bias humans use when looking at each other. Dogs became exquisitely sensitive to human emotional tone, body language, and even the direction of eye gaze. But none of these sophisticated social adaptations overwrite the caching behavior. A dog can learn 200 human words, perform complex multi-step obedience routines, and read the emotional state of her owner from across a room. And she will still bury a bone in the garden when nobody is looking. The social cognition and the caching instinct exist in entirely separate neural networks. Domestication reshaped the social circuits dramatically. It left the subcortical survival circuits almost untouched. If you ever wondered how that is even possible, consider the architecture. The canine brain, like all mammalian brains, is built in layers. The deepest and oldest structures, the brainstem and basal ganglia, govern basic survival functions. Breathing, heart rate, sleep cycles, and fixed action patterns like caching. These structures are sometimes called the reptilian brain, though that label oversimplifies the evolutionary history. They are ancient, and they are resistant to change, because any mutation that disrupts them tends to kill the animal outright. You cannot tinker with the brainstem the way you can tinker with the cortex. The margin for error is too thin. Layered on top of that is the limbic system, governing emotion, social bonding, and memory. Above that sits the neocortex, responsible for learning, problem-solving, and behavioral flexibility. Domestication primarily reshaped the limbic system and the neocortex. It made dogs more social, less fearful, more attentive to human signals, and less independently motivated. But it did not reach down into the basal ganglia and rewire the motor programs that had been running there for tens of millions of years. It could not. The architecture does not allow it. Those programs are too deep, too protected, and too disconnected from the social circuits that domestication was actually reshaping. This is why your dog does something that looks irrational. The behavior was rational once. The environment changed. The behavior did not. For a while, things actually seemed fine. For thousands of years after domestication began, dogs still experienced enough food variability that caching probably maintained some marginal utility. Early dogs were not fed on schedules. They scavenged from human refuse piles, competed with other dogs for scraps, and experienced lean periods during famines that affected their human companions. The caching instinct would have continued to pay off, however modestly, for most of the domestication timeline. The truly anomalous period is the last 150 years. Reliable commercial dog food only became widely available in the mid-1800s. James Spratt, an American electrician living in London, introduced the first processed dog biscuit in 1860. Before that date, dogs in most of the world ate whatever they could find or whatever scraps their owners threw them. Predictable, measured, nutritionally complete feeding is a phenomenon that occupies less than 1% of the dog's domestication history. Less than 1%. 160 years out of at least 15,000. From the perspective of the dog's genome, reliable feeding has existed for an evolutionary eye blink. Natural selection has not had enough generations to even begin reducing the caching behavior, even if reliable feeding were somehow harmful enough to create selection pressure against it, which it is not. A dog that caches bones in a modern household faces no survival penalty. There is no reason for the behavior to disappear. The parallel to other vestigial behaviors in domestic dogs is instructive. Dogs circle before lying down, a behavior that in wild canids served to flatten grass, check for snakes, and orient the body relative to wind direction. Dogs scratch the ground after eliminating, a territorial scent-marking behavior that serves no purpose in a backyard but fires the same interdigital gland scent deposition sequence that wolves use to mark territory boundaries. Dogs howl at sirens because the frequency profile of emergency vehicle sirens happens to overlap with the howl frequency range of wolf long-distance communication calls, roughly 150 to 780 Hz. The siren is not a wolf. The dog's auditory processing centers do not know that. Each of these behaviors is a ghost, a behavioral fossil preserved in neural tissue rather than stone. They persist not because they serve the animal, but because nothing in the animal's current environment selects against them strongly enough to eliminate them across the necessary thousands of generations. But this wasn't just about dogs. The pattern extends across every domesticated species on Earth. Domestic cats still stalk and pounce on toys with the full predatory sequence: eye, stalk, chase, pounce, kill, bite, even when they have never experienced hunger and will never need to catch prey. The sequence is encoded in the feline basal ganglia, just as caching is encoded in the canine basal ganglia. A house cat with a full food bowl will still murder a mouse and leave it on your doorstep. Not because it is hungry. Because the motor program runs independent of nutritional state. Domestic horses still spook at snake-shaped objects on the ground, a predator avoidance response from a time when horses lived on grasslands full of venomous reptiles. A horse that has spent its entire life in a stable with no exposure to any reptile will still leap sideways at a garden hose coiled in unexpected grass. The fear response is not learned. It is inherited. And it has persisted through roughly 6,000 years of domestication, since horses were first broken on the steppes of what is now Kazakhstan around 3500 BCE. Domestic chickens still perform the full predator alarm call system documented by ethologist Chris Evans at Macquarie University in Sydney during the 1990s. They have distinct calls for aerial predators versus ground predators, triggering different escape behaviors in flock members. A chicken that has lived its entire life in a coop with no predator exposure whatsoever will still look up and freeze at the silhouette of a hawk passing overhead. The visual template for raptor shape is innate. It was burned into galliform neural architecture long before humans began keeping chickens around 8,000 years ago in Southeast Asia. What domestication changes is the threshold. Wild wolves cache almost everything surplus. Domestic dogs cache sometimes, and some breeds more than others. Terriers and dachshunds, bred for underground pursuit of burrowing prey, tend to dig and cache more readily than retrievers, whose breeding history emphasized holding objects in the mouth and delivering them rather than burying them. The instinct is present in all dogs, but the strength of its expression varies based on what other behavioral programs have been layered on top of it through selective breeding. Friederike Range and Giuseppia Veragni at the Wolf Science Center in Ernstbrunn, Austria, have spent years conducting comparative studies between wolves and dogs raised in identical conditions. Their work, published in journals including Frontiers in Psychology and Current Biology through the 2010s and into the 2020s, has illuminated exactly which behavioral differences between wolves and dogs are due to domestication and which are due to rearing environment. Wolves raised with constant human contact from birth still cache food with high reliability and intensity. Dogs raised in identical conditions cache less frequently and with less precision. The domestication process did not eliminate the behavior, but it appears to have reduced its motivational priority. In wolves, the presence of surplus food triggers a near-compulsive caching response. In dogs, the trigger is weaker, more easily overridden by competing motivations like social engagement with a human or simple laziness. The program is still there. It just fires less reliably. Range described it as a difference in threshold rather than a difference in architecture. The machinery is identical. The activation energy required to start the machinery running is higher in dogs than in wolves. But give a dog the right stimulus, a high-value resource, a moment of solitude, a suitable substrate for digging, and the ancient program runs exactly as it did on a frozen Siberian plain 20,000 years ago. Pay attention to this next detail, because it explains everything about why the behavior looks so strange in a modern context. Dogs do not cache food when they are hungry. They cache food when they are satiated. This is counterintuitive but critical. A hungry dog eats. A full dog, presented with more food than it can consume, buries the surplus. The behavior is not driven by deprivation. It is driven by abundance. In a wild wolf's ecology, this makes perfect sense. You do not bury food when you are starving. You eat it immediately. You bury food when you have more than you need right now, because the future is uncertain and surplus is temporary. The wolf that buries when full retrieves when hungry. The wolf that eats everything immediately and buries nothing has no reserve when the next hunt fails. But in a domestic dog's life, this triggering condition creates a paradox. The dog is always full. Every meal arrives on schedule. There is never genuine scarcity. But occasionally, the dog receives a high-value item, a bone, a chew, a treat, that exceeds what it can consume in one session. The abundance trigger fires. The caching program activates. And the dog buries a bone she will never need to dig up, because another meal is already measured out and waiting. The dog is not confused. The dog is not stupid. The dog is running ancient software on modern hardware in a modern environment. The software was never updated because there was never a reason to update it. It still works, in the sense that it executes without error. It is just solving a problem that no longer exists. And that might sound like a purely animal phenomenon, a quirk of non-human cognition, a limitation of the canine brain that human brains have evolved past. But that assumption would be wrong. Consider what happens in your own body when you eat past the point of fullness at a holiday dinner. Your ancestors survived famines that killed millions. The ones who ate maximally when food was available, who stored calories as fat with ruthless metabolic efficiency, were the ones whose children survived the next drought. That caloric hoarding instinct is your version of the buried bone. You are caching energy in adipose tissue against a famine that, in the developed world, will almost certainly never come. The food scarcity is gone. The metabolic program is not. Or consider anxiety, the human stress response, the cortisol spike, the racing heart, the hypervigilance. Evolved to keep your ancestors alive when a predator was stalking them through tall grass. That system fires identically when you read an aggressive email from a coworker. The threat circuitry does not distinguish between a leopard and a message notification. It responds the same way it always has. The predator is gone. The amygdala is not. The golden retriever burying a bone in a flower bed and a human being lying awake at 3 a.m. worrying about a quarterly report are exhibiting the same fundamental phenomenon. Ancient neural circuitry designed for a world that no longer exists, running in a body that lives in a world the circuitry cannot comprehend. The environment changed. The wiring did not. Jessica Heckman, a veterinary geneticist who has studied canine behavioral genetics at the Broad Institute of MIT and Harvard, has explored how specific genetic variants influence behavioral tendencies in dogs. Her work contributed to a large-scale 2022 study published in Science by Kathleen Morrill and colleagues that analyzed the genomes of over 18,000 dogs and found that breed explains less than 9% of behavioral variation in individual dogs. 9%. Meaning that the behavioral differences between a border collie and a beagle are far smaller, genetically, than most people assume. But the behaviors that are shared across all breeds, the deep ancestral behaviors like caching, like circling, like the startle response to sudden movements, those showed almost no variation by breed at all. They are canid universal. They are the bedrock that all the breed-specific variation sits on top of. The fancy hat that selective breeding placed on the dog's head did not change the skull underneath. If you have ever watched a dog push her nose along a carpet, shoving invisible dirt over a chew toy she placed in the corner of a living room, you are watching 35 million years of canid evolution execute a motor program in an environment that is unrecognizable to the programming. The dog's nose pushes against fabric where it once pushed against loose soil. The covering motion completes even though nothing is being covered. The sequence terminates. The reward circuit fires. The dog walks away satisfied. She is not protecting the toy from competitors that do not exist. She is not preparing for a winter that central heating has abolished. She is completing a behavioral loop that produces a dopamine reward upon completion. The behavior has become its own purpose. Means have become ends. The survival strategy has transformed into a compulsion indistinguishable from habit. Alright, so here is where things get genuinely interesting. Some researchers have begun asking whether caching behavior in domestic dogs might actually be increasing in certain populations rather than fading away. The logic runs like this. Modern pet dogs often live in environments saturated with high-value objects. Dozens of toys. Multiple types of treats. Bones, chews, stuffed animals, rubber balls. A wolf might encounter surplus food a few times per month after a successful hunt. A well-equipped pet dog encounters surplus triggering stimuli daily. The caching program, which in a wolf fires occasionally and purposefully, may be firing in domestic dogs more often than it ever fired in their wild ancestors, simply because the triggering conditions are met more frequently. The behavior is not fading, it is being stimulated at an accelerating rate by an environment that accidentally provides exactly the conditions that activate it. More stuff means more triggers means more caching. The suburban home, with its abundance of chewable, buryable, cacheable objects, may actually be a more potent activation environment for the caching instinct than the resource-scarce wilderness where the instinct evolved. Which, looking back, was either incredibly ironic or incredibly predictable, depending on how you think about evolutionary mismatches. There is a final dimension to this that dog owners rarely consider. Wolves who cache food also retrieve it. The retrieval is the entire point. A wolf buries meat in November and digs it up in December when the pack has failed to kill for 2 weeks. Cache and retrieve form a functional pair. One without the other is meaningless. Domestic dogs cache but rarely retrieve. Studies of pet dog behavior, including observational research conducted by canine behaviorist Alexandra Horowitz at Barnard College in New York, have documented that many dogs appear to forget where they buried items, or simply never return for them. Owners discover buried toys weeks or months later while gardening. The bone stays in the ground indefinitely. This suggests that the retrieval component of the behavior has degraded more than the caching component, and that makes evolutionary sense. Caching is a fixed motor program, a hardwired sequence that fires on trigger. Retrieval requires flexible spatial memory, a cognitive skill that wolves maintain through constant practice and necessity. Domestic dogs who never need to recall cache locations because their next meal arrives regardless may have lost the motivational drive to maintain that spatial memory. The program that buries is still intact. The program that remembers where is atrophying. It is the behavioral equivalent of a factory that stamps out products and drops them into a warehouse, but the shipping department closed years ago. The products pile up. Nobody moves them. The factory keeps running anyway. And the running is the point, not the product. The dopamine fires when the bone goes into the ground. It does not need to fire again when the bone comes out. The reward circuit has lost its connection to the original survival outcome and become self-reinforcing. Bury. Feel good. Repeat. This is what tens of thousands of years of domestication look like from the inside of a brain, not the clean removal of outdated software, not the rational optimization of behavior toward current conditions, but the slow, messy, incomplete disconnection of ancient programs from their original purposes, leaving the programs intact but purposeless, firing on triggers that no longer signify what they once signified, producing rewards for actions that no longer produce results. Your dog buries bones because her genome remembers a world where surplus was temporary, competition was lethal, and winter could last 6 months. That genome does not know about climate-controlled houses. It does not know about measured kibble portions. It does not know that the bone is safe in the garden because no wolverine will ever find it, and no blizzard will ever prevent a return trip. The genome carries only the instruction that was written by 2 million years of canid survival on a planet where starvation was the default and food security was a temporary illusion that ended with the next failed hunt. The dog cannot read the instruction, she can only follow it, and she will keep following it for as long as dogs exist. Because the environment that wrote the instruction disappeared 15,000 years ago when the first wolf walked toward a human campfire instead of away from it. But the instruction itself is still being copied, letter for letter, into every puppy born in every litter in every home on every continent where dogs live alongside humans. 20,000 years of domestication. 360 million pet dogs alive today, a population roughly equal to the entire human population of the United States and Western Europe combined. Every single one of them carries the caching instruction. Every single one of them, given the right trigger, will push dirt over a bone with a nose designed to track wounded elk across frozen tundra. The behavior is not disappearing. It is not even weakening, not on any time scale that matters to the individual dog or the individual owner watching from a kitchen window. Evolution does not move at the speed of human observation. It moves at the speed of differential reproduction across thousands of generations. And in a world where caching behavior carries no reproductive cost, there is no force pushing against it. No selection. No pressure. No correction. The instruction persists because nothing erases it. The bone goes into the ground because the genome says so. And the genome is very, very old. It remembers ice, it remembers hunger, it remembers the wolverine. It remembers the 6 weeks between kills when the pack grew thin and the cached haunch of caribou, frozen in shallow permafrost and retrieved by scent memory alone, was the only thing standing between the pack and starvation. The golden retriever in the backyard does not remember any of this. Not consciously, not in any way she could articulate if she had language. But her motor cortex remembers, her basal ganglia remember, her dopamine system remembers. And so she digs, and so she buries, and so she trots back inside, satisfied by the completion of a task that solved a problem she has never faced, in a world she has never inhabited, for a future that will never arrive. The instruction was written in the Pleistocene. It is still being read today. The only thing that has changed is the ground. If you want to see more videos like this one, click the video on the screen now.